Hello and welcome to this session on overlapping generations models in a small open economy. So in the last video, we looked at material from my book, Public Economics. We looked at the overlapping generations model with growth and with endogenous labor supply and estimated, well, an optimal pension system should be approximately be characterized by a replacement rate of around 18%, meaning that pensions should be about 18% of gross wage income during working life. Now, this is much lower than in the United States presently. It's about half of it. And we wonder how robust are our results with regard to the assumption that we considered a closed economy so far. So what we do in this session, we extend our model of a closed economy to one of an open economy. And we have to be kind of restrictive here. We look at a small open economy. So this doesn't necessarily apply to the United States, which is a large economy and has an effect on the world interest rate, the world wages. We have something in mind like a small country like, for example, Belgium or Switzerland. So let's assume we look at a small economy and look what happens in this economy if we abolish pensions, or what's the optimal pension replacement rate, the ratio of pensions to gross wages, and we will find that it falls to zero. It's best to have no pension system at all in a small open economy, at least in our simple model. And I will explain it to you why and what kind of changes are necessary in our overlapping generations model to consider an open economy. So let's get into the slides. Overlapping generations model of a small open economy. So in section 6.35 of my book, Public Economics, we studied optimal pension policies in an overlapping generations model of a closed economy. We had exogenous technological progress, so labor augmenting technological change. And we had endogenous labor supply, and we found that the optimal gross pension replacement rate of pensions amounts to 19%. While the current replacement rate of pensions is 39% for the mean income in the United States. In this video, I will look at the small open economy, and the basic result, the astonishing result, will be the optimal replacement rate of pensions falls to zero. So it's better for the government not to provide any pensions at all. And let me tell you how I get from the model of a closed economy to one of a small open economy. So for these reasons, I need to make a couple of assumptions here. We look at a small economy, so there's no effect of this country on the world interest rate R star, which is given exogenously in international capital markets. We assume perfect capital mobility, meaning that if the interest rate is lower in the domestic economy, we invest our money abroad, and vice versa. If interest rate is above R star, money will be invested in our country, so that in equilibrium, of course, the interest rates are equal, so that the domestic interest rate R is equal to the world interest rate R star. For this, we also assume that domestic and foreign assets are perfect substitutes, which is also a very simplifying assumption. We assume that domestic and foreign goods are perfect substitute. This keeps us from introducing a real exchange rate. So our real exchange rate here is simply 1 because they are perfect substitutes, foreign goods and domestic goods. And we assume no labor mobility, so that if the wages are abroad are higher, that workers leave the country and work in the country with higher wages. Now we still keep the simple structure of a two-period overlapping generations model. So in the first period, we work LT hours, labor supply is endogenous, and in the second period, we retire and receive a pension. So period length is approximately 30 years, but of course, this is very simplifying here. So we work usually twice as long as we remain in retirement. So a 3-period model would be more accurate to describe what's happening in the empirically. But we keep it simple. So just 2 periods. First periods we work, second periods we retirees. In the first period we contribute to the social security system, the pay-as-you-go system, and the retirees in this period collect the social security contributions and get a pensions. And in the next period, when we get old and retire, we receive a pension which is financed by contributions of the young generation. So we have a pay-as-you-go pension system. And we assume that the number of people grows at the rate n. So let NT denote the number of young households, and it grows at the rate n over time. And then also total population, which is the sum of the young people NT plus the old people NT minus 1, also grows at the rate n. We have a production sector, just like in the case of the last video where we looked at technological progress. So we have a production sector with labor augmenting technology factor 80 that grows at the exogenous rate gamma. That's the consistent way to introduce technological progress in the model as labor augmenting. If we had a production function that's not Cobb-Douglas but has a different substitution elasticity, different from one, then the only one that's in accordance with long-run growth facts is labor augmenting technological growth AT. And we set gamma equal to 0.8, so approximately 2 years annually. That's what we observe for the United States for the last 30-40 years. Now, firms maximize profits, which is production minus wage cost minus interest rates cost minus depreciation. Uppercase KT is the capital stock, NTLT is the hours we work, and AT is our technology factor, WT is our wage. And we have the standard first order condition that our wage is equal to the marginal product of labor, and the interest rate R is equal to the marginal product of capital minus depreciation. And lowercase k here is a new variable, which is simply aggregate capital stock per effective worker. Now, in the open economy, we have to distinguish gross national product and gross domestic products. So gross domestic product is the outcome of our production process, what is produced domestically. But we might also have income from abroad. For example, if we hold foreign wealth, we get an interest rate which is equal to the international interest rate R star. And this foreign wealth is denoted by NFA, net foreign assets. So for example, in the United States in the year 2020, according to data by Schmidt, Grohe, Uribe, and Woodford in their undergraduate textbook on international macroeconomics, the net foreign assets, or rather net foreign debt of the United States was 67% of GDP. Now, and gross national product is the sum of GDP plus interest income from our foreign wealth or our interest minus our interest payments for our foreign debt. National wealth is defined as our aggregate capital stock plus our net foreign wealth, our net foreign assets. And as evidently, if our savings are, if our net foreign assets are below zero or negative, then our wealth is below the aggregate capital stock K, and some of the capital stock, the domestic capital stock, is owned by foreigners. We impose a no Ponzi game constraint, meaning that we cannot accumulate an infinite amount of debt, NFA, in the long run. So if you come, for example, from a simple model, a two-period model, then you would know, well, at the end of period 2, the world ends. And so we know that at the end of 2, we would get no credit, no debt from foreign countries. So therefore, we would have the condition that at the beginning of period 3, when the world has ended, there would be no debt left that we have to repay to foreign countries. Now, if you extend this kind of condition to infinity, then you get this no points a game constraint that is shown here in the last inequality on the slide. Well, this will not be a problem in our model, because in our model, as we find out, in steady state, our net foreign assets will grow at the rate gamma, at the rate of the technological progress. And our star will be larger, our real interest rate will be larger, will be picked at 3%, will be larger than the growth rate of our net foreign assets, which will grow at 2%. So this condition is fulfilled in our model. Now the rest of the model is fairly straightforward, and you might know it from the previous sections of my book, Public Economics. So we have a lifetime utility that's additive in utility from consumption as a worker, C1T, as a retiree, C2, T plus 1, and we have a disutility from working, which is additively here, and we have a fresh labor elasticity, new 1, which characterize our reaction to a change in the wage rate by how much we increase our labor supply. The budget constraints are given in equations 70a and b and c. So our income, which is wage, WT, time AT, times the hours we work, LT. Well, we have to pay social security contributions at the rate tau on this gross wage income. And we can use it for either consumption as a worker, C1T, or save it, ST. Now in old age, we get the savings plus interest rate, and we get a pension T plus 1. If we solve equation 78b for savings and substitute it in equation 78a, we can derive the intertemporal budget constraint 78c. So our present value of total consumption is equal to the present value of total income. Okay, so let me just briefly show you the timing in our model here so that you can understand our notation here. So we live in period T, we are worker, and in period T plus 1 we are retiree, we are retired. We work over the period T, and at the end of the period we get our wage WT, LT, AT, and we have to pay contributions tau T to the social security system. Now part of this income we consume at the end of the period T, and part of it we save, and at the beginning of period T plus 1 we invest our savings either domestically in the capital stock of the firms, or abroad in the form of net foreign assets. And over the period T plus 1, we receive the interest R star or RT plus 1 on our savings ST. And at the end of the period T plus 1, again, we consume in old age, and we also get a pension at the end of the period, which we use for consumption. So that's the timing in our model. Now we can derive the first order condition by setting up the Lagrangian function. And let me just interpret the first order condition. So condition 79 simply states that the Lagrangian multiplier is equal to the marginal utility of consumption as a worker, 1 over C1T. According to equation 80, this is our first order condition with respect to consumption in the next period, and condition 81 is our condition on the optimal labor supply. Now we can substitute lambda from these three first order conditions and derive equations 82a and b. So the first equation, 82a, is our Euler condition, meaning that we compare saving 1 unit, then we get the interest rate 1 plus RT plus 1 on this savings. we get utility 1 over C2 t plus 1 in the next period, but we discount this utility by the factor beta, or we do not save this extra unit of good, but rather consume it today, then we get utility 1 over C1t. That's our first order condition with respect to savings, our so-called Keynes-Ramsey rule or Euler condition. And the second equation is our optimal labor supply condition. So on the left-hand side of equation 82b, we have the disutility from working, the marginal disutility. If I work an extra hour, that's my loss in utility, my marginal loss, nu 0 times L to the power 1 over nu 1. And on the right-hand side, we have the gain in utility. Well, working an extra hour, I get an income 1 minus tau WT 80. And this gives me the marginal utility 1 over C1t, the extra utility, by multiplying it with the marginal utility 1 over C1t. And if we stationize our individual variables, we divide them by the labor productivity factor AT, which gives us equation 83 and 80A and B. Now we can solve our equations for the optimal savings. So we substitute our Euler equation into the intertemporal budget constraint. This gives us an expression for C1t, and then we substitute C1t in the definition of savings, which is derived in the final two equations on this slide. And again, we make this equation stationary by dividing by aggregate productivity AT. Okay, now let's look at the capital market equilibrium. In capital market equilibrium, our aggregate savings, the savings of the young at the end of period T, are used for either invested in the capital stock in the domestic economy, and if I have extra savings, then I invested abroad, so resulting in positive net foreign position, or if my savings fall short of the aggregate capital stock, well, then foreigners will invest in the domestic economy because of international arbitrage, so that the interest rates are the same internationally. And if I divide this capital market equilibrium condition by AT and NT, then I derive that savings in efficiency units, AT/NT per effective labor, is given by KT plus 1 plus NFA-T plus 1 times 1 plus gamma times 1 plus N, where lowercase NFA are simply net foreign assets divided by effective workers AT/NT. Okay, and to close the model, I have to describe the pension system, and we run a pay-as-you-go pension system, so that the contributions tau times WT AT/LT, so the contribution rate tau on my gross wage income WT AT/LT times the number of workers NT is spent on NT minus 1 retirees, and they all receive the pension. And if I divide this by AT, I can derive the stationary pension level, pension tilde, which is 1 plus N times tau times WT LT. So in the United States, the contribution rate is about 12% tau. And if I look at the gross replacement rate of pensions in our model, which is the pension level divided by gross wage income, well, then it's 1 plus N times tau. There is an inconsistency because I only look at a two-period model. So we have the contribution rate of 12% in the United States, but according to the gross replacement rate is 39% in the United States, implying a value of tau approximately equal to 0.35, so much higher. And I have to choose how I calibrate it in my model. I will put tau equal to 30%, so somewhere in between the social security contribution rate and the gross replacement rate of pensions. But that is a necessity because I look at such a simple two-period model. To be more accurate, I should look at an, let's say, 60 or 80 period model and use annual periods rather than 30-year periods. Okay, and if I summarize all these variables, all these conditions, and look at a steady state where the variables are constant, well, I derive these 7 equations here in 7 unknowns. So the Euler equation with first equation, second equation is our first order conditions on labor supply, third equation is wages equal to marginal product. Fourth equation is that the interest rate, which is equal to the world interest rate R star, is equal to the marginal product of capital minus depreciation. Fifth equation is the capital market equilibrium. Sixth equation is balanced budget of the social security. And the seventh equation is our intertemporal budget constraint. Now let me point out a special feature of the overlapping generation model. So here we have a steady state system and 7 equations and seven unknowns. Perfect. That's what you would like to have. You would like to have the same number of unknowns and equations to solve for this model. Now, a problem that shows up when you use the Ramsey model and infinitely lived agents in an open economy, for example, a book that considers the infinitely lived agents, the Ramsey model, is the one by let me show you this, by Martin Uribe and Stephanie Schmidt-Grohe. Well, then you have a problem when you look at an infinitely lived model. Let me show you this in our first order conditions here. Consider the first equation. Now, if you look at a representative agent, infinitely lived household in steady state. Now, in this steady state, consumption is constant, meaning that C1 and C2 are equal and drop out. So you lose one condition to pin down your endogenous variables. You are short of one condition. This does not happen in the overlapping generations model because C1 and C2, the consumption in young age and the consumption in old age as a retiree, are different. Therefore, we do not lose one endogenous condition here for our steady state and do not have a problem. So the way you solve this in these open economy models is you introduce a closing condition. So for example, one possible closing condition is that you specify the interest rate as a function of the world interest rate and a premium on your debt. So if you have high debt and strongly negative net foreign assets position, well, then the world, for example, demands a higher interest rate. And this way you introduce again a 7th endogenous equation for your steady state here and for the dynamics as well. Now, in our overlapping general equilibrium model, we do not have to resort to this trick, to this necessity. Another way to get around this necessity, well, is pointed out in the book by Alfred Mausner and me, Dynamic General Equilibrium Modeling, which came out in 2024, the 3rd edition. And there we consider also a business cycle open economy model with infinite lived households. Well, and because we do not solve it with perturbation method, but with extended path method, we can circumvent some of the problems. So perhaps you like to look at this as well. 3rd edition, 20-year-old book, but still I think some people like to use it in their graduate work. All right, now how do we calibrate the model? As I said, we used a period length of 30 years. We use production elasticity of capital of 36%, implying a wage share of 64%, approximately what you observe in the United States, even though it has been declining over recent decades a bit. We assume that capital depreciates completely 100% because we look at such a long period of time, 30 years. We have an annual growth rate of 2% for our labor augmenting technological progress, which will also be the steady state growth rate in our model. We assume population growth rate of 10% over the 30-year period. And we calibrate the parameters mu1 of the utility function and beta, the discount factor, so that in steady state labor supply is equal to 30%. So we work 30% of available time of 1, and the real interest rate is equal to 3%. So we come up with a solution here for nu1 and for beta. Notice that our beta is above 1. Well, that's no problem here in our overlapping generations model. In the Ramsey model and the infinitely lived household model, you cannot use a value above 1 because then the utility becomes infinite. But here in our model, well, look at the utility function ut. Even if beta is above 1, no problem. It's a finite value for ut. Okay, we set the replacement rate equal to 30%, which is kind of a compromise because we have such a simple model with just 2 periods. So the social security contribution rate in the United States is about 12% currently. The replacement rate is about 39% in the United States. So we should pick something in between, but it's of course there's an error. If we should make more accurate predictions about policy, we need more periods in this model, like in our Burkhard model with 60 or 70 or 80 periods. Now our calibration implies that our real interest rate, 3% annually, is higher than our growth rate of 2% and growth rate plus population growth rate. And this results in a dynamically efficient economy, meaning that if we reduce savings, consumption does not increase. So I've described this material extensively in previous videos and in my book on public economics. So please look up this case of dynamically efficient economy. And there's some evidence in the data provided by Helen, Mariels and van Lemmenhove in the Journal of International Money and Finance in 2024. And here you see, in this graph, you see for different country groups, the difference between the real interest rate and the growth rate. And as you can see that, for example, for the core European countries, the solid one with the black squares, the real interest rate is pretty much always above the growth rate until 2014 or 2015. Same holds for Anglo-American countries, the dotted line. Now, in recent years, it has declined so that the real interest rate became lower than the growth rate, except for the COVID-19 years here, 2018, 2019. And the two authors make the prediction, well, that our baseline expectation is that R minus gamma will stay below 0 for the next 2 decades in most European countries. So meaning that these countries become dynamically inefficient while the United States remains dynamically efficient. Okay. Now let me get to the results. So I've used these 7 nonlinear equations in the 7 variables to calibrate the model, and then I run an experiment. I decrease the social security contribution rate from 30% to 0%. And I looked what's happening to welfare, and welfare is measured here by the utility function, in particular by how much I can increase consumption C1 and C2T, or have to decrease it as I reduce pensions. And let me show you the results here for the closed economy. The closed economy is the blue line. So we start at a contribution rate of 30%, and as I reduce it, we find that welfare increases to approximately 6.7% of consumption. So I can increase consumption in each period as a worker and a retiree by 6.7% if I get rid of the pension system. Now, this positive effect from the pension, from abolishing the pension system, of course, stems here from the tax wedge on the labor supply. Because of the social security contribution, this first order condition is distorted I reduce my labor supply because of the distortion in the form of social security contributions, and therefore welfare is lower. And if I increase it, well, this increases. If the social security contributions decreases and the tax wedge declines, then welfare increases. Now, this is not the case in the closed economy that we considered in the previous video. And why is this the case? Well, the first effect that if I reduce pensions and then the distortion in the labor market declines and increases welfare is also present. But here then in the closed economy, savings increase incredibly by a huge amount, and therefore the interest rate drops below the dynamically efficient interest rate, below the golden rule that the interest rate should be above the growth rate. No, it turns around in this range here. Interest rate falls below the golden rule level, and then our welfare declines because we produce in a dynamically inefficient economy. So, and this effect is bigger than the reduction, the distortion in the labor market. All right, so from this picture, please notice that it's crucially important that you consider these kind of sensitivity analysis. Look at an open economy when you do welfare considerations of pension system. Now, let me show you the effect on net foreign assets here. Net foreign assets, well, as households increase their savings here in this economy, as I reduce the social security contribution rate, the tax on labor's income, well, they increase savings, and as a consequence here in our model, wealth goes up and wealth increases beyond the capital, the domestic capital stock, and they purchase foreign assets, so net foreign assets go up to 9% of GDP if I get rid of pensions. I calibrated the steady state so that net foreign assets in the initial steady state are zero. Okay, to summarize the results here, if I abolish a pay-as-you-go pension system, savings increase by 7% because households have to accumulate higher old age savings, but this is much smaller than in the closed economy. There we computed an increase of savings by 133%. Same calibration, but just closed economy. So factor price adjustment makes a huge difference in our welfare consideration. And we still have huge welfare effects here, 6.7% of total consumption if we abolish pensions. Now, the optimal steady state pensions in the open economy is 0%. In the closed economy, it's 18.8% because the interest rate in the closed economy falls below the golden rule level. Now, so to summarize, if you study pension system in small open economies, like for example in Belgium, please consider the sensitivity analysis of a small open economy. It might have very different results. In the United States, if you consider a large economy, well, the assumption that the world interest rate is not affected by the United States, of course, does not hold. So therefore, this should just provide some additional information here, the open economy solution and welfare analysis, but it's not as important as in the case of small economies. If you would like to have the slides, ask me questions, would like to have the code, please send me an email and I will be happy to forward you the code. So thank you for your attention, and I hope this will help you to set up your own open economy model with overlapping generations.